Hello and welcome to day 3 of my Advent of Code 2024 review in ARM assembly for the Game Boy Advance. So let's have a look at day 3's problem. We are at a warehouse. There's a computer trying to run a program, but it's corrupted. Looks like the program's goal is to multiply some numbers. So we're looking for instructions that look like x, open bracket, mul, open bracket, x, comma, y, close bracket. The two numbers in a multiply instruction, right? X and y are each 1 to 3 digits in length. So because it's been corrupted, there are invalid characters that should be ignored. For example, mul, open brackets, 4 star, asterisk, right? Ignore it. Mul, open brackets, 6, comma 9, nice. With an exclamation mark instead of a close bracket, ignored. Numbers in brackets but missing the mul, ignored. Or mul space, open bracket space, 2 space, comma space, 4 space, close bracket, ignored. Right? It has to be compacted, right? No extra characters. So for example, we have mul 2, 4, that gets multiplied. Mul square brackets 3, 7 is ignored. Mul 5, 5 multiplied. Mul open bracket 34, 64 closed square bracket ignored. And 2 more muls that are multiplied over here. Right? And for part 2, because we'll look at part 2 as well. For part 2, there are 2 more instructions. Do, in brackets, enables the mul instructions. The following future mul instructions. Don't, brackets, disables the following mul instructions. Right, so only the most recent do or don't applies. At the beginning of the program, mul instructions are enabled. So in this case, looking basically the same as before, we have this don't here, and so because of the don't, we don't multiply 5 times 5, and we don't multiply 11 times 8 until we hit this do, and then we multiply 8 times 5. Right. So for part 1, we multiply all the muls. For part 2, we skip certain muls that are between don't and do statements. Alright, so let's have a look at the code, shall we? So today we have, we're all on the internal RAM again. We have our ASCII num, we're still using ASCII num. We have an X num and a Y num. I'm going to store those in the RAM. We have some comparisons we're looking for. This here is an ASCII representation of MUL, open brackets, backwards. So we've got M, U, L, and then here is the open bracket, ASCII 28. It's backwards, don't worry about it. And we've got one for do, same sort of thing. DO, DO, open brackets, close brackets. For don't, I've split it into 2 parts because don't is a little bit long. We have D, O, N, apostrophe, T, open brackets, close brackets. Got 7 characters. So you have DO, there's a little bit of overlap here. DO, N, apostrophe, N, T, open bracket, close bracket. In the ASCII representations. I'm going to use those to check for these markers in the input. So we go into our main loop for solving the day. Register 8 is going to be the start of the input, register 9 is the end of the input. When we're within 4 bytes of the end, there's going to be no more data, so we can just end it there. Here's our things for part 2. R11 is whether we are multiplying well, whether we're adding the multiplication of the mulls, the result of the mulls to part 2 or not, whether mull is enabled. R4 is for our don't, and I'll explain that in a second. And we go into our read loop. So now I've changed how I'm doing the read loop a bit. R8 is just our reading offset. We'll increment R8 all the time, right? We don't have to use R10. We're not adding them together or anything. We're just looking at R8. Is R8 the same as R9? I've got greater than or equal to. If it is, then we finished the day, right? We finished the input. So next we set R1 to 0 and R5 to 3. R5 is our offset, and I've got this small loop here, get 4. So what we're going to do, right, all our checks are going to be checking 4 bytes, and normally what you'd like to do is just read a word from the input. But in ARM, if you read a word from, you have to read words, 4-byte segments, from memory aligned to that 4-byte alignment, 4-byte alignment. So we'll say, like, let's say you're at the very beginning of memory at index 0. You have to, and you read a 4-byte word, you'll get in order 0, 1, 2, 3, those indexes. Now if you try to read from, say, index 2 a word, in your register you'll get the values from 2, 3, 0, 1. Right, you'll get it rotated around that position that you're reading from, because it's not aligned with the 4-byte segments. So that's what I wanted to do. I wanted to read words and just look at it, but you can't do it like that. So instead, what I am doing is just reading 1 byte at a time and logically shifting it left 8 bits each time I read one. Well, before I read it in, I logically shift the register left 8 bits, 8 places, and then read the byte and add the byte, addition, add the byte to the register. And that way I get 4 bytes into the register. And then I'm going to compare what's in the register to those comparators above. So first thing we're going to do, I'm going to stop deleting lines. We're going to compare, we're going to look at R4. If R4 is not 1, then we do skip don't. If it is 1, then we change R4 to 0, because the first part of don't has been checked, and we're going to check the second part of don't, the second half of don't. Now it turns out that in the input there are no I could have just checked for DON apostrophe, because the only cases of that are completely don't ones. There are no DON apostrophe K or anything like that. So I didn't need to have the second check, but it makes it so it is resilient, I guess. So if R4 is 1, I have read in DON apostrophe, and now I'm checking to see if what's in the register now is apostrophe T open bracket close bracket. So do that check. If it matches, then R11 becomes 0, and we branch to the increment offset. If it isn't, well, we just keep going, right? It could be, maybe we're seeing the beginning of a mull, so we fall into this part here. So the next thing I'm checking for is we're comparing to the do comparator. do open bracket, close bracket, right? Compare that. If it is, if I delete lines again, if it is that, we move, we make R11 1, so we enable the mulls for part 2, and we branch the increment offset. Otherwise, we check to see if the first part of don't, if it's the first part of a don't, right? If it is the first part of a, if it isn't the first part of don't, we go to try mull to see if it's mull. If it is the first part of a don't, we increase the offset by 3, so it will start at the apostrophe. We set R4 to 1, so we've seen the first part of a don't, and then we branch into reloop instead of increment offset. I could have done add 2 and then go to increment offset. It doesn't matter. Otherwise, we check to see if we've seen the first part of a mull. Does the register contain MUL open bracket? If it does, we branch into eval mull. If it doesn't, we go increment offset. And eventually, we'll get to the end of the input, and we branch to finish day, and that's the end. Right, so let's check eval mull, shall we? Eval mull. So we've got into an eval mull. We've seen MUL open bracket. So what are we doing? R4 becomes 0. We add another 4 to our offset. Because we've backed up the registers R8, when we leave eval mull, R8 will return to what it was before we entered this subroutine. So we can keep using it without overriding the original. We load our ASCII num. We're using ASCII num again as usual, and we load the length of it into R4. Right, the number of values we've stored in ASCII num so far, which should be 0. And we also load pointer to xnum into R10. Right, and we go into our loop. So we load a byte from R8, our offset of the input. If it's a comma, then we need to check if we're splitting we check val split. We're checking if we are, wait a second. If we've got a comma, we check we've got a valid left number. I don't think I'm actually doing that in check val split. Well, we do effectively check that. Yeah. This is actually that comment I wrote before I made it into check val split. I think I had check val num originally. I think I originally had check val num down here, and I put in check val split because originally I was just checking to see if there was a comma and then seeing if we had a valid number in the ASCII num. And there were cases in the input where a mull had more than one comma in between the brackets. So like mull xyz instead of mull xy. Because I wasn't checking that it was only one comma, it would incorrectly multiply that one and would give me the wrong result. So that was a bug that I had early on. So this is why I've got check val split here. I'll go over that in a second. The next check, we'll be checking is it the closing bracket? We might have the second number, so we'll that goes to a check there. Next, we check to see if the byte we just loaded is a value, an ASCII value less than 30, which means it's below the 0 in the character in the ASCII table. If it is, we're leaving, right? And then we check to see if it's greater than 39 in the ASCII table, which is ASCII character 9. If it is, then we're leaving, right? It's not a valid character. Assuming we get through those checks, we load the ASCII num value. Alright, yeah, we load the ASCII num value. The pointer value, we compare it to 3 because that will tell you the current length of the number in ASCII num. So if we've already got a 3-digit number in ASCII num, we're trying to put a 4th digit in there, it's not valid anymore, we end the evaluation, we just jump out. Otherwise we add 1 to the offset, we create our binary encoded decimal, and we store the number into ASCII num and the new offset, and increment our offset for reading the input, and then branch back up to the start of the loop again and keep loading numbers, right? So let's say we have seen a comma. If we've seen a comma, what we want to do is check R4. If R4 is not equal to 0, then we are ending eval num. We're ending this evaluation. R4 will be 1 once I have first seen a comma. So if it's not 0, then we've seen a comma before, and this is the second comma, and we're getting out. It will then fall into check val num if it has passed this check. The next one, check val end, for seeing the closing bracket. This I'm also checking to see if R4 is 1. Right? Have I seen a comma? Have I seen a comma? If it's not a 1, we're getting out. Right? We've only seen one number. And if we pass that check, we just branch straight to check val num. Okay? Alright. So in check val num, we're loading our length of ASCII num. Again, we check to see that if it's 0, if we haven't loaded any number into ASCII num, right, then we branch out, we get out. Otherwise, we convert it to ASCII. We've seen this before, basically the same. And we store, actually, we might have to look at this. We'll branch. So if we have a number in ASCII num, we'll branch to convert ASCII. So let's have a look at that. Down here again. It's much the same as before. The difference here is that the value will be returned in R0. So right, I don't back up R0 at the start of the subroutine, and I don't restore R0 at the end of the subroutine, so the value of R0 will be returned from the subroutine. So R0 is going to be where we store the result. R3 is our multiplier, R4 is our 10 multiple. Loading the ASCII nums and the offset, we're loading each value from ASCII num, we multiply it by the multiple, we add it to the result, we multiply the multiple by 10, move it in there, and then we go to the next number in the loop, and then we clear out the offset, the length of ASCII num at the end of the convert ASCII. And see, we're finished. We've got the value in R0 when we go back to here. So we store that value of R0 into R10, which is xnum. Right. Then we check R4. If R4 is 1, we have both our numbers, and we can go to do mull nums. If it is not 1, we make it num. If it's not 1, we make it 1. And then we load into R10 the address of ynum. And then we increase our offset and branch back to loop renums. Right? So the second time coming through this check val num, we should be branching to do mull nums, or we would be getting out for some reason. Right? And so we go into this do mull nums. Right, we take the values from xnum and ynum, and multiply them together. R0 has the result. We add it to result 1. Right, we load the result we load the address of result 1 into R5. We load the value in result 1 into R1. We add R0 to R1, and we store R1 back into R5. Then we check R11. If R11 is 0, then we don't multiply, we don't add the result to R2, result 2. So if R11 is 0, we're not doing the part 2 result, and we'll just branch to end eval mull. Otherwise, we add R0 to the result 2 as well. We jump to end eval mull, and we are done. We'll end up back in here, where we'll increment the offset and keep going through the input. And then once we finish the end of the input, would end up at finish day. And that's all of the code for part 1, part 2, day 3. Alright, so let's have a look at it running, shall we? Let's run the code. Here we are, we've got our day 3. Yep, let's run it. Bonk. And there's our result. Alright. No problems there. Pretty quick. The memory view is not so interesting this time, but let's have a look at it anyway. So, what do we have? Up the top here, we have our ASCII num somewhere about here. And our x num and y nums are hanging out around here, and the result R1 and result 2 are still updating every frame, hanging out down here. So we'll just run this again, pass numbers, and it's done. Yep. All right. So that's day 3. Day 3 is completed. We're going at a good pace this time. Alright, so I hope to see you back again for day 4. I think things are going to get a little bit more difficult. But until then, catch you next time.